Good morning, everyone. Thank you for joining us today.
Good morning. Great to be here.
Last time, we took a deep dive into edge computing and fog in IoT, looking at how processing data closer to the source, can really change the game for efficiency. Today, we're taking that journey a really crucial step further, because let's be honest, all that data collected at the edge, maybe in the cloud, it's just a flood of ones and zeros, isn't it? It's like crude oil, loads of potential, but, pretty useless until you refine it. So our mission today is to unpack the alchemist's art, data analytics, and visualization for IoT. We're diving into how we turn that raw digital stream into, actual wisdom, actionable insight. This is key for anyone wanting to grasp how companies really use IoT to compete globally. Okay, let's unpack this.
Yeah, it really is the essential next step, isn't it? I mean, without figuring out how to interpret and act on the data, the whole IoT thing kind of loses its punch. It's definitely where the rubber meets the road.
I couldn't agree more. And it really seems like at the heart of almost every IoT setup, there's this one fundamental type of data, time series data. Could you maybe unpack that for us? What is it exactly, and why is it so central to IoT?
It's fascinating, actually, how fundamental time series data is. So simply put, it's just a sequence of data points collected one after another. At regular time intervals, think of it like a continuous feed of information streaming from sensors, watching the physical world. It's just the natural output when you're tracking how things change over time.
Okay, so not just a single picture, but like a movie.
Yeah.
A constant flow.
Yeah.
What makes it different from, say, just a list of products in a warehouse?
Exactly. It's got some key characteristics that really set it apart. First, every single data point is tied to a specific moment. It's time-stamped. And that's not just a minor detail. It's foundational for analysis. Second, you're dealing with high volume and velocity. Just picture one industrial machine, maybe dozens of sensors, each spitting out data every single second.
Wow.
Or, a whole smart city with millions of sensors, you end up with this just immense amount of data arriving incredibly fast. And third, it's almost always append only. New data just keeps getting tacked onto the end, the old data. It rarely gets updated. And this append-heavy nature, it really impacts how you design the databases for it.
That makes total sense. Like monitoring someone's heart rate. You're always adding the new beats. You're not going back to change yesterday's reading.
Yeah.
So with these unique features, how does that change how we store and handle all this data? Can traditional databases keep up?
Well, you see pretty quickly why the usual suspects, like general-purpose relational databases, MySQL, for example, they're often just not the right tool for IoT at scale. They just weren't designed for that relentless, append-heavy, super-fast workload where time is the main way you look things up.
Right.
So this led to the rise of specialized databases. We call them time series databases, or TSDBs. Think things like InfluxDB, Prometheus, AWS TimeStream. These are specifically built, optimized for sucking in massive amounts of time-stamped data really quickly. And for running those time-based queries efficiently, like what was the average pressure here over the last day?
Okay.
What's fascinating here is it really shows how the nature of your data dictates the kind of storage you absolutely need.
That distinction is super important. Specialized tools for a specialized job. But okay, even with the perfect database, there's that old saying, right? Garbage in, garbage out. So before we can even dream of getting wisdom out, how do we start refining this digital crude? What needs to happen before the actual analysis? Here's where it gets really interesting.
You've absolutely hit on a critical point there. Before you can do any meaningful analysis or visualization, that raw data stream has to be cleaned up, prepared. Raw sensor readings, they're often really noisy, full of random jumps and fluctuations that can totally hide the real signal you care about. This is where data filtering comes in. A common technique is using something like a low-pass filter. It basically lets the slow, steady underlying signal through, but blocks all that high-frequency static or noise. You end up with a much cleaner, more interpretable data stream, like finding the actual heartbeat through all the interference.
Okay, so filtering cleans up the static. What about data smoothing then? Is that similar, or is it doing something different?
Smoothing is more about revealing the underlying trends within that cleaner data, which might still be a bit, jumpy. Most common method you'll see everywhere is the moving average. Think of it like paving over a bumpy road. You're still on the same road, but the ride's much smoother, the overall direction is clearer. So maybe a 10-point moving average on temperature data. That would help you see the daily heating and cooling pattern much more clearly, instead of getting lost in tiny second-by-second changes. If we connect this to the bigger picture, It's not just about making the line look prettier, it's about intentionally stepping back a bit, maybe blurring the immediate now to actually see the important patterns over time.
That's a great way to put it. Smoothing out the bumps to see the road. And what about those points that just stick out like a sore thumb?
Yeah.
The really weird ones. I mean, outliers. How do we handle them? Are they just bad data points we throw away?
Outliers, yes. They can be tricky, but also incredibly important. An outlier is basically a data point that's way off from everything else. They can be caused by sensor errors, glitches in transmission, sure. But sometimes they are genuine critical events, like a sudden massive pressure spike right before a pipe bursts.
Oh, wow.
So dismissing them as just noise can be dangerous. Identifying them and figuring out why they're there is absolutely crucial. Ignoring a critical one could mean missing a vital early warning.
So they could be errors or they could be super important signals. How do we tell the difference? How do we spot them reliably?
We generally use statistical methods, things like the z-score, which basically measures how many standard deviations a point is away from the average.
Yeah.
If it's, say, more than 3 standard deviations out, that's often flagged. Or the interquartile range IQR method. These aren't just random math. They give us a solid, quantifiable way to spot those significant deviations.
Okay, so we can mathematically identify them. Then what?
Then you have choices, depending on the context. If it looks like a clear error, maybe you remove it. Or you could replace it, perhaps with an estimated value, like the moving average. But if it could represent something critical, you absolutely flag it for immediate investigation. The potential impact really dictates how you handle it.
Okay, that's a really thorough look at getting the data clean. Data hygiene, as you said. So once it is clean, pre-processed, we humans, we need to see it, right? Turning numbers into something intuitive. So how do we translate all this refined data into stories we can understand? What are the key visualization tools people use in IoT?
Right. This is where we make the data accessible. And when you're talking about real-time operational monitoring, the big name you'll hear constantly is Grafana. It's really the leading open source platform for this. It's hugely popular with DevOps teams, site reliability engineers, IoT developers, anyone needing to watch system health and performance live.
I've definitely seen Grafana dashboards around. What makes it so good for IoT specifically?
Its main strength is its flexibility, its versatility. It plugs into tons of different data sources, especially those specialized TSDBs we talked about, InfluxDB, Prometheus, and so on. Perfect match there. And it lets you build these really beautiful, highly customizable, real-time dashboards. You can have graphs, gauges, heat maps, world maps, whatever you need. Plus, it has a pretty powerful alerting system. You can set rules, and if a metric crosses a line, boom, you get a notification on Slack, email, PagerDuty, whatever. It's invaluable for staying ahead of issues. It basically turns those data streams into a living picture of what's happening right now.
That sounds perfect for the operation side. But what if you're, say, a business analyst, maybe less focused on the second-to-second system status and more on the bigger picture? Like, how does this IoT data fit with sales figures or costs?
Yeah, different need, different tool. That's where something like Microsoft Power BI really shines. While Grafana is awesome for those operational views, Power BI is a market-leading business intelligence BI tool. It's designed for broader business analysis and reporting. Its real superpower is integrating that IoT data with other business data sources. Financial data, sales data, marketing data, whatever. It pulls it all together to give you that holistic view of business performance. It's built more for business analysts, letting them create rich, interactive reports that really bridge the gap between the technical sensor data and what it means for the bottom line. Less what's happening now, more why does this matter to the business overall?
That makes sense. Different audiences, different tools. And what about maybe developers who are just starting out or someone needing to quickly mock something up? Like, is my sensor even sending data without setting up a whole big platform?
Yeah, for that rapid prototyping scenario, Node-RED is incredibly useful. It was actually developed by IBM's Emerging Technology Services group. It's got this visual, flow-based programming interface. You literally drag and drop nodes and wire them together. And it has a dashboard module that lets you whip up a simple web UI gauges, charts, buttons really, really quickly. We're talking minutes sometimes. So it's perfect for just proving a concept, visualizing some basic sensor data quickly, maybe adding a little control without the overhead of Grafana or Power BI. Great for quick tests and proof of concepts.
Okay, Grafana for ops, Power BI for business analytics, Node-RED for quick prototypes. That covers a lot of ground. So we've gone from raw data to cleaning it to seeing what's happening and what has happened. That's a massive improvement in understanding.
Yeah.
But What about the next leap? Predicting what will happen. This is where machine learning enters the picture, right? Moving from looking back to looking forward.
Exactly. This is the really exciting part. Machine learning, or ML, is the key that unlocked that shift from just reacting to problems to actually being proactive and even predictive. At its core, ML algorithms learn patterns from historical data. Then they build a model based on those patterns to make predictions about new future data. This is how we get that alchemical transformation data into actual foresight.
Okay, so ML helps us predict. Where do people usually start with ML in IoT? What's a common first step and maybe a really impactful example?
Probably the most common starting point, and honestly, a real killer app for ML and IoT, is supervised learning. In supervised learning, you train the algorithm on a data set that's already labeled, meaning the historical data includes the correct answers you're interested in.
Okay.
So for IoT, the classic example is predictive maintenance. Imagine you have years of sensor data from machines' temperature, vibration, pressure, whatever. And crucially, you know which periods of operation were healthy and which ones eventually led to a failure. You label the data accordingly. You feed this labeled data to a supervised learning algorithm. It learns the subtle patterns that precede a failure.
Right.
Then, that trained model can analyze the live sensor data coming from a running machine and predict the probability of it failing within, say, the next week or month. This lets you schedule maintenance before the expensive breakdown actually happens. It's about seeing the trouble coming.
That's incredibly valuable. Preventing downtime, saving costs, huge. But what if you're dealing with something new? Maybe a system where you don't have years of labeled failure data. How do you find patterns then in the unknown?
That's a great question, and it leads us to unsupervised learning. Here, you give the algorithm unlabeled data. Its job is to find hidden structures or patterns all on its own without predefined answers. A very common technique here is clustering. The algorithm tries to group similar data points together automatically. In the IoT world, a primary use case for this is anomaly detection. You can train an unsupervised model on data collected during the device's normal operating state. It essentially learns the signature of normal. Then, when new data comes in, if a data point doesn't fit that learned pattern of normalcy, the model flags it as an anomaly. Something unusual is happening. This is super powerful for catching completely new or unexpected kinds of failures or issues, things that weren't in your historical data because they've never happened before. It's about spotting the weird stuff you didn't even know you should be looking for.
Finding the unknown unknowns. That's fascinating.
Okay, so supervised for known outcomes, unsupervised for finding the unusual. And then there's the third one, reinforcement learning. This always sounds a bit like sci-fi machines learning through trial and error. How does that apply in a practical IoT setting?
Yeah, reinforcement learning, or RL, it's definitely advanced, but it enables a really high level of autonomous optimization. The basic idea is you have an agent, like a piece of software controlling something. This agent operates in an environment, takes actions, and gets feedback. Positive feedback or rewards for good actions, and negative feedback, penalties for bad ones.
Like training a dog, almost.
Kind of. Over many, many cycles of trial and error, the agent learns a policy, a strategy for taking actions that maximizes its total accumulated reward over time. A really cool IoT example is HVAC optimization in a smart building. An RL agent could control the heating, ventilation, and air conditioning. Its goal: minimize energy consumption, that's the reward. But it has to do it while keeping the building within comfortable temperature ranges. For people staying outside those ranges gets a penalty. Right.
So the agent tries different heating and cooling strategies. It learns the building's unique thermal dynamics, how quickly it heats up, cools down, where the hot spots are. And over time, it can discover a control strategy that's way more energy efficient than any set of rules a human could have programmed manually. It's about systems that learn to adapt and optimize themselves.
Wow, a system that truly learns and adapts on its own. That's amazing. This has been just an incredible journey, really, from raw data bits to this idea of proactive, predictive intelligence. It really drives home that data analytics and visualization aren't just, one step in the IoT process. They feel like the destination where the actual tangible value gets created.
Absolutely. I think the key takeaways are, first, recognizing the unique nature of that high-velocity time series data and knowing you need specialized tools for it. Second, the absolute necessity of that rigorous pre-processing, cleaning, filtering, handling outliers. Remember, garbage in, garbage out is so true here. Then we saw how powerful visualization tools like Grafana for operations or Power BI for business insights turn all that abstract data into stories humans can actually understand and act on. And maybe most importantly, That introduction of machine learning marks this huge shift, right? From looking backwards, hindsight, to looking forwards, foresight, enabling systems that can predict failures, spot anomalies, and even intelligently optimize themselves with things like reinforcement learning.
It really feels like the ultimate goal is creating this continuous real-time feedback loop, doesn't it? Between the digital world of data and the physical world of machines and environments, constantly driving improvement. But looking ahead, what are the big challenges? What's next for this alchemist's art?
Well, the challenges are evolving. It's less about just collecting the data now. It's increasingly about ensuring the quality of that data, guaranteeing its security and privacy, which is huge, and honestly, finding the skilled people, the data scientists, the engineers who can build, deploy, and interpret these complex analytical systems, that's a major bottleneck.
A talent gap, yeah.
And looking further out, imagine the fusion. Sophisticated analytics, more advanced ML, combined with AI running right there at the edge. This convergence could lead to systems that aren't just connected, they're genuinely cognitive. They can understand their environment, predict what's coming, and act autonomously. That's the direction towards creating a safer, much more efficient, and ultimately more sustainable world, all powered by intelligent IoT.
A truly cognitive future. That is a powerful thought to end on. Thank you so much for this incredibly insightful deep dive today. And thank you, our listeners, for joining us as we explored IoT data analytics and visualization. Hopefully you have a clearer picture now of how those ones and zeros get transformed into real-world wisdom. We definitely encourage you to keep digging into these transformative technologies. The journey is really just getting started. Stay tuned for our upcoming series on Internet of Things, security, and privacy. Thank you for listening, and please consider subscribing to our channel, Tech AI and Beyond, for more deep dives. Until next time.